Okay, hi everybody. We're ParaDocs, and thank you for coming for our preliminary design review. So, in one sentence, our project description is a robotic solution to assist in total knee replacement. We're doing this by improving on existing robotic solutions by targeting four major user needs. First, presently, IR trackers are used for tracking, but they're bulky, they're invasive, they're basically hammered into your bone for tracking. So our user doesn't like them, and we're going to be replacing them with RGBD cameras. Secondly, these IR trackers require an IR camera to be placed away from the surgical site, and that interrupts the line of sight, and the surgeon needs to work around it. So our vision-based solution is twofold by actually preventing the need by being mounted directly on top of our manipulator. Thirdly, our user wants us to automate this process of actually drilling holes for knee replacement. And that's why we're going to autonomously plan a trajectory to the site of drilling and actually do the drilling autonomously as well. Fourthly, it is important to compensate for any motion that the patient might have. So even when they're sedated, they might actually move the knee, which has happened before. So to compensate for that and any other obstacles that may arise, we need to account for that. So that's where what our project description is. But how we imagine it in the use case is that suppose a patient decides that, a surgeon decides that they need to operate on a patient's knee. They are the ones who will begin the surgery by actually orienting the patient in flexion like this and cutting open the skin to expose the bone. That is when Technica will actually come into picture and sense where the bone is, locate the site that they want to drill at, go to that site, drill, avoid any obstacles, compensate for motion. And once it has drilled the holes, it will be wheeled out of the OR. And then the surgeon will again come into play by sliding pins into these holes and placing the implant for replacing the patella. So from a project description, we came up with 13 functional requirements, and each of them is augmented by at least one, and sometimes two quantitative performance requirements. So we've been over this before, but I'd still like to highlight our functional requirements quickly. We will be sensing the surgical site as a point cloud. We'll register the surgical site, obtain the desired drilling pose, generate the trajectory to move to the drilling position. This entire time, the system should be tracking the surgical site in real time. It will compensate for any bone motion. It will actually drill the holes as well. And just for the UI, it will be visualizing visualizing what the camera is seeing, and also take in commands from the UI, such as going to home position, stopping motion. It will avoid any obstructions that are present in the surgical site. And in case of any emergency, through a physical e-stop, it will stop the procedure. How we actually envision these functional requirements in diagrammatically, I think I would like to call Kimi to present the architecture.
Thank you, Shubhangi. And our functional architecture is basically the same as the last semester, but let me briefly recap it. And to better understand it, imagine our system as the well-organized orchestra, where every section plays a critical role here. Let's start with the inputs. We begin with the pre-stored surgical plane, the digital twins of the pre-operative bone model, and the real-time data we collect of the patient bones and the surgical sites. With all these visual information, we first do the sensing jobs at the perception stage, where we generate 2 point clouds, one for the obstacle avoidance and another one used for registrations, and which is then used for calculating the desired drilling pose and depths. With these coordinates, we then do the trajectory generations to ensure the precisions, and it is also designed to compensate for any patient's movements in real time. And as the extrication stage, we actually move the end effectors to the drilling sites. We move it to the drilling post and perform its task, drill on the femurs and tibia. And no worries, this stuff is always prepared here for safety insurance. And for the outputs of our systems, and these two folds, and the physical with the drilled femurs and tibias ready for bones implants later, and the visualized outputs ready for the monitorings for the surgical teams. Yeah, while the functional architectures provides us on the blueprints of what our system should do, our cyber-physical architectures focus on how to implement these functions by the combination of the software, hardware, and the process. Start with the surgeon IO. The three basic commands we provide for the commands is the start, stop, and the home. The perception stage here is tedious, but no worries. And our perceptions experts, Abhishek, will walk you through to get familiar with this later. And for planning, we're generally using moving to generate the trajectories. And for the extrications, only 2 points we need to notice here. For the arms controls, we're using the LBR servers provided by the ParaDocs controllers to control the motors. And for the drills controls, we're using GPIO to control the drill drill. As for the system and subsystem descriptions, hand it to Param.
Hi. Okay. So we split our system into three basic subsystems: the drilling subsystem, manipulation, and perception. So the drilling subsystem refers to the end effector, which basically includes the drill machine, the camera and drill mounts, and of course all the cables that go with all of it. So the desired state for this subsystem is that the end effector can be controlled via ROS for drilling. We had a choice between the form factor of the drill machine. So we landed up choosing the one where the motor is connected to the tool via flex shaft so that we can reduce the weight on the end effector. We mount the drill motor separately. So this is what the current status is. This is what the end effector looks like mounted on the KUKA with the drill and camera on it, and the drill mount is on the side there. As for interfacing, we have this is what our PCB schematic looks like. We have begun getting the parts and trying to build it on a proto board to test it out. The next subsystem is the manipulation subsystem. This is basically referring to the planning and control stack. Basically, everything that goes into getting the end effector to the position that's required by perception. Desired state is, of course, that our drill bit can reach the global coordinates and execute drilling. So for this, we are using, this is basically what the structure looks like. We have the entire compute with perception, mover for planning, and the client on our system, the ROS2, which then talks to the KUKA controller. This connection took us a bit to figure out with like the sponsor and KUKA support, and it's an achievement. We figured it out. This is where we currently are at. If we can give the simulation of poles and Arvis and move it, can plan and execute it on the actual robot. Which brings us to the next subsystem, which is perception. Abhishek.
So this is what we are finally aiming for, to have a 2-camera setup with a top-down D435 that will be used for dynamic compensation and motion tracking. But that is not our current focus. So for this semester, we'll only be using the D405 and the registration pipeline. This is what the raw point cloud from our D405 looks like. As you can see, there's a lot of noise and artifacts, so we need to filter them out before we can attempt registration. And to simplify our work, what we did is we collected a data set of 22 different samples of RGB plus depth plus point cloud with the bone and camera in different positions. The idea being is that if we can constantly register across all these scenes, our pipeline is robust. Our current pipeline itself consists of 3 stages. First is extraction, that is removing all the noise and just extracting the bone region. Second is estimation of global registration, which is to get the initial alignment. And finally, it's using ICP-based methods for refinements. So we tried a variety of different methods from different libraries and even some learning-based methods. But what worked out for us in the end, as you can see in bold, is a custom heuristic and also just fine-tuning classical methods. So we found out the long and hard way that classical methods are classic for a reason. This is what our pipeline looks like. We first do a manual crop that just removes most of the artifacts. Then we use ransack plane segmentation to remove the table. Then we use clustering, and then we just pick the largest cluster, which is usually the bone. Then we give the initial alignment based on a heuristic that we found out it empirically works well for us. Then we don't directly do ICP once because that simply didn't work out. We combine it with ransack, where we do 200 trials. And for each trial, we add some noise and we start with a different initialization position. And in the end, we pick the one with the best alignment. So these are our final results. It's still not perfect. We're still working on it, but we're constantly able to register on 12 out of the 16 samples that we have. And we're still working on it. And this is what it looks like in the context of our overall point cloud. This entire stack is currently, this entire pipeline is in Open3D. On the raw side of things, we have started developing a pipeline where we can get the data, and we've also done hand-eye calibration. Now it's just about connecting these two subsystems together. Now I'll hand over to Live, who's our project manager.
So when it comes to project management, let's first take a look at our original breakdown structure. So the certain IO and integration and the management will remain the same, but we did some update on the subsystems. So the cross-out thing is the thing we already done, but the highlight text is the new work package. So we will have more focus on the registration on bone specific segmentation to boost our registration. And also we have been having more time on interfacing the drill because PCB is the thing we are not very familiar with. We need more time on that. So when in terms of schedule, we're already done with milestone 1 and 2, that is workbench ready and A factor. And we're currently working on milestone 3 and 4. For milestone 4, we're on track and we can finish on time. But for hookah arm and drill control on milestone 3, because the PCB is kind of blocking us, we are trying to learn it. So we are behind about a week of schedule. So this is the entire schedule from spring semester to fall semester. And the only update we did is that we put milestone 8, dynamic compensation, forward because we expected we will spend more time on it. And in terms of our high-level testing plan, before SVD, our arm should be able to perform the drilling motions, and our perception pipeline should already be integrated with manipulation. And also, the E-stop will be ready for safety concerns. So in the SVD, we will have end-to-end drilling, but there are some assumptions. I will talk about that later. So for a high-level test plan in fall, at the end of August, we will try to rerun the spring test again to make sure our system is working fine. And at the end of September, our surgeon IO should be ready, and we will be doing TBR registration. For now, our registration is all on Filmer, but when it's end of September, we're working on TBR registration, and also the dynamic compensation that is not integrated with Vision. But by the end of October, our dynamic compensation system will be integrated with the Vision, and we will reach our performance requirements on drilling accuracy. So in the FVD, we'll present end-to-end autonomous drilling. So here's a more deep dive into SVD and FVD. In SVD, we have some assumptions that we're only using one camera, we're only drilling one hole on Filmer, and it's an end-to-end. So there's no motion and no dynamic compensation. But in the FVD, we'll have our both cameras online to track the bone motion, and we'll be drilling multiple holes both on Filmer and TBR. So for SVD and FVD, the sequence is basically the same. The only difference is the bone motion and the drilling holes on TBR Filmer. So the test location will be B512. And the robot the sequence of events is that the robot will be at a standby state. And once commanded, the robot will move the end effector to the drilling position and start drilling. After drilling is done, the robot will retreat back to its home position and wait for next command. So our quantitative metrics is our requirements and also our tests relevant to the validation. So finished schedule, let's move on to budget. We spent around 15% of our budget, and we mostly spend them on equipment acquisition. And we are expecting to buy more bone models because we need them for testing, registration, and drilling. And here comes our risks. Some of them have already been resolved, but I still put them on. But we also did some updates because as we start working on a project, we find out that the risk is that some group member might be absent because of illness or burnout or have an interview. So we always have a primary and secondary assigning for each task, so they can cross-reference to each other and help each other. And we also find out a risk is that our code might have version conflicts or data loss. So we set up a version control software, Git and GitHub, and also back up all the binary files onto Google Drive. So this is the risk, likelihood, and consequence table before mitigation and after mitigation. So that's all for our presentation. Thank you, and break it out.
Okay, super job, great job, fantastic. A few questions, okay. The first one is, maybe I'll start from the SVP and explaining my notes here. How much control are you going to apply on the drilling portion and demonstrated in the spacing?
By control, you mean?
I mean, is there anything at low level that will control the drill? How much will you do drilling?
Yeah.
How much of that drilling will be controlled? Like,
Yeah.
Autonomous?
yes.
Yeah, I can do that. So, ideally, we're planning to make it completely autonomous for one hole. So we would be able to send like a ROS command to turn on the drill and actually drill it. So that is what we are aiming for, and we're just a little bit off track because the PCB is taking some time. In the worst case that we're not able to achieve that, we have a foot pedal that we can actuate with. So we will definitely drill a hole, but yeah, like we might do it manually in case something fails in the PCB. Also because we want to make sure the e-stop is working before we autonomously drill something.
We'll discuss more business about this.
Yes, yes.
Okay. All right. The next thing then is, so you're focusing specifically on the operation of the bone, and then you're leaving kind of the quality of the workspace, if I understand it correctly, for the whole semester, like
Yeah.
imagine everything else.
Yeah.
Do you have a sense on how much those two things actually kind of create dependencies on each other? Do you expect, for instance, that the patient is going to be fixed in one location and the surgeon follows within sequences, so you can place the camera and you always have a clean area to see. Only this all makes sense, right? But how much understanding do you have actually about the environment and how the two things actually relate? The two things is the bone and the kind of the unobstructed.
Yeah, we haven't explored that area much about how much the involvement of the top camera will be. We know it could be useful, but for example, for tracking, the top camera has a better view, but it may not be able to pick up small motions. So then we may end up relying on the D405 itself for tracking motion. So we still don't know the degree of dependence between who does what, but the workspace, obstacle avoidance and stuff will be on the top camera. That's the,
Yeah, that should be very interesting because it may affect obviously the cost of that.
Yeah,
You'll
yeah.
save in the whole semester. And then, just very quickly, regarding yes, I didn't see much of integration in all the software we get integrated and stuff. Maybe I missed it, but certainly we just make sure we think about this integration process a little bit more. And I guess the last question we have time on it. The last question is, so your perception pipeline work is great. I mean, so great results. I mean, it's area. I'm wondering, though, how much the fact that this bones are going to be less in the body of somebody would affect kind of the segmentation or the way you segment it. You said, okay, we find the biggest thing is the bones, and then we segment that out.
Yeah.
What happens if the bone is not there? It's not going to be there by itself. It's not. It's going to be in a person. I'm wondering. Do you think there's another layer of analysis needs to be done on the perception aspect?
I think the bone, at least in the videos you've seen, it's pretty cleanly visible because they completely remove this flesh and it's clearly there. The current problem we are stuck on is that the whole pipeline, it extracts both the bones, both the femur and tibia, and that messes up our registration.
Oh.
So the next step is segmenting just a specific bone, and that's what we're trying to figure out right now.
Okay. Yeah, I just had a high level question. Obviously, there's a lot of the research to affect the second program, but safety in general, have you thought about that? And one thing that I think we're going to talk about really is the singularity and the singularity and getting such a robot.
Yeah, that's one of the problems. And another problem is that, as you saw, the motor mount it's not attached on the arm; it's separately there. So the robot's motion is inherently limited. So we're hoping to do very small motion so that in a very constrained workspace so that we know we don't run into singularity issues. In terms of safety, the biggest concern is obviously the drill. Let's say the manipulator goes haywire and the drill is on, bad things could happen. So the biggest thing is we're not giving full autonomous control to the drill until we know the e-stop and everything's working. That's currently what the safeguard that we have in place.
All right, we can open up for the minute, almost 2 minutes of questions and time. You guys are all ready to go on, sorry. Okay. Oh, there we go.
Just for like, what you guys consider like background stuff? So if we like to start watching, they need to like for whatever reason. Stuff.
What's it?
So background stuff.
Oh, I see.
Enabling. It's an enabling switch. You need to keep pressing on.
Oh, like on Tesla or we didn't.
So, but a KUKA pendant has an inherent, it has different modes, and one mode is like you have to press like 3 different buttons to keep
Yeah.
operating it. You let one go, it stops. So that's the.
We did spend a lot of time going away from that road, so we might not want to get back.
Do you have a good sense of the requirements on the accuracy of the drilling?
Yeah, I think we have.
So overall, the sponsor said that they wanted to be within 2 millimeters and at the most 2 degrees of angle, but we plan on trying to do that for every week.
Okay. Where the surgeon points to, or?
So the idea is that we have the bone model, and the surgical plan is marked on that bone model, which is why the registration is. So that's
Yeah.
Do you have like the model of that person's knee or like a generic?
So the eventual goal is that you have to be able to do it on a generic model, but to begin with, the sponsor has told us to, well, the sponsor told us to make it with the specific model, but our goal is to be able to do generic.
So coming back to the accuracy thing, it's like even if visually the registration result looks correct, even if there's a slight deviation, the whole system goes off. So that's the biggest concern that we have right now. I'm happy to say.
Sorry.
Awesome.
Thanks.